Hello, everyone. Welcome to the lab on measurements of space and time. So in this lab, we will do a few things. One of those is we will measure the density of a small aluminum cylinder that's in your kits. Like physically, if you do this, your aluminum cylinders in your kits and lab. Um, and while we do that, we will also practice calculating measures of accuracy and precision, which we learned in the other handout and the other videos, right? Calculating how to calculate PRAD, which remember is a measure of precision, and then how to calculate percent experimental error, which is a measure of accuracy. Okay, so in the first part of the lab, we're going to ultimately measure the density of aluminum cylinder. But to do that, we need to measure the mass of the cylinder and the volume, right? If you remember, density is equal to mass divided by volume. So let's start with measuring the volume of a cylinder. So if you think about it, right, a right circular cylinder has both a diameter, right, or a radius. You can think of the diameter as being twice the radius, and a height. So we need to measure those two lengths. We need to measure the diameter of the cylinder and then the height of the cylinder. To do that, we're going to use an instrument called the vernier caliper. And the vernier caliper is a fairly accurate instrument. It has a resolution of zero point zero 0.01 centimeters. So the smallest length that it can measure is zero point zero 0.01 centimeters. So the first thing I'm going to do is show you guys how to read a vernier caliper. You'll have some vernier calipers in lab that you can use. In this video, I'm just going to use a simulation to show you how to read the vernier caliper. Okay, so let me go to that screen. Okay, so here's a vernier caliper. And if you notice, there's basically two scales on a vernier caliper. You have the main scale, which goes along the vernier caliper, and this is in centimeters. And then you have another scale, which is called the vernier scale, which just goes from 0 to 9. And this is on one of the jaws that moves. So this is the vernier scale. This is the main scale. So let's say we want to measure the length of this blue object here. So the first thing you would do is you would place the object between the jaws of the vernier caliper, right, and close this down. So you'll do that when you're measuring the diameter and the length of the cylinder, aluminum cylinder. And then to read the length of this, what you do is you read where the zero is. Sometimes this is also called the index, the zero here. So where is that zero, the zero on the vernier scale? Where is that located on the main scale? And notice here, right? So this is one, right? Or you can think of it as 1.0, 1.1, 1.2, 1.3, 4, 5, 6. So it looks like the zero is past the 1.6, but not quite 1.7. In fact, it's a little bit less than halfway, right? Between 1.6 and 1.7. So we know it's going to be 1.6 something. To get that last digit, the hundredths place, what you do is you look on the vernier scale and you ask yourself which line, which number, 0, 1, 2, 3, and so on, lines up best with any marking from the main scale here. And if you look at this, first of all, just by eyeballing it, because it's less than halfway, it's probably going to be like 1.62, 3, or 4, somewhere in there. So if I look on the vernier scale now, it looks like actually the 3 lines up best. So then I would read this as 1.63 centimeters. That would be the length of this object. Okay, and actually that's what the computer does it over here. That's what it's also getting 1.63. Let's do a few more of these. Let's say this is the length. Okay, let's say this is the length of the new object. So again, I want to read where the zero is on the main scale. In this case, it's past 2.1, right? Because this marking would be 2.1 and not quite 2.2. Eyeballing it, it looks like it's a little bit past halfway, so it might be 2.16, 17, 18, somewhere in there. To get that last digit exactly, I look on the vernier scale. And sometimes this is difficult to do. Sometimes you kind of have to guess. But in this case, it looks like the 7 lines up pretty closely with the main marking on the main scale, right? It looks like it's the best. Nothing else really lines up well. So, and we know it's kind of going to be 6, 7, or 8 anyways, just by eyeballing it. So in this case, sorry, it's a 0 here, right? So 6, 7, or 8. So in this case, the reading would be 2.17 centimeters. 2.17 centimeters. All right. Let's see. Okay, let's say this is another object, right? We want to measure this length. And let's say we get this particular reading right here. So how would we read this? Well, if I look at the main scale, where is that 0? Well, it's at 2.2. And then in this case, the 0 lines up best, right? Because it's right on it. So actually, you would read this as 2.20 centimeters. And you have to give that 0 for the hundredths place, right? So it would be 2.20. Okay, let's do one last one. Let's say this is the length you want to measure. In this case, the 0 is just past the 2. Okay, so the first part would be 2.0. And then to get the last digit, well, it looks like it's maybe halfway, maybe a little bit more than halfway. So I want to focus on like 5, 6, or 7. And I'm going to argue that 6 lines up best. So actually, this reading would be 2.06 centimeters. Okay, that would be that length. So in lab, it's exactly the same thing, except obviously with a real vernier scale, sometimes it's a little bit difficult to read because the numbers are so small, but it's exactly the same idea. Okay, so the first question that you're going to be responsible for from the lab manual is question 4. And if you look at this lab, basically this is lab 1 in the lab manual from Polito, Walsh, and Gagnon, the 10th edition. And basically, it's just going to ask you to explain in words how you use the vernier caliper to measure the diameter and the length of or the diameter and the height of the small aluminum cylinder. So you're just describing in words how you did that measurement. Okay, so you're going to take 5 measurements of the height, 5 measurements of the diameter, right? Again, all these values will be to 2 decimal places, right? Because remember the resolution is 0.01 centimeters for the vernier caliper. And then question 5 is basically to, first of all, you want to give all your data. So you want to fill in this entire table here, right? And make sure you include it in your lab report with your particular data, your particular values in here. And question 5 is going to ask you to compute the average height, the average diameter. So basically, you have to add up your height values, divide by 5, and make sure, this is important, make sure you round to the resolution of the instrument. So round to 2 places. Same thing for diameter. And then it's also going to ask you to compute the prad for height and the prad for diameter. Okay, and to compute prad, remember we went over that in a previous handout and in a previous video as well. So if you don't remember how to do that, make sure you look that up again or watch the video again. So you're going to calculate prad for height, prad for diameter, right, as a percentage. Okay, question 6 is going to ask you to compute the volume of the cylinder and the prad for volume. So to do that, let me jump over to the tablet to help you with this, to explain how this works. Okay, so again, we have a right circular cylinder, right? The aluminum cylinders are right circular cylinders where they have a radius and a height. And we know that to compute the volume of a right circular cylinder, and draw on the base here, which is also a circle, the volume is simply going to be the area of the base, right, which is a circle. So it's going to be pi r squared times the height, right? That will be the volume of the cylinder. However, we're not measuring the radius, right? We're measuring the diameter, but there's a simple relationship, right, between the radius and the diameter. Remember, the diameter, I'll call it d, is twice the radius, so 2 times the radius. Or if I solve that for r, I can write this as the radius is half the diameter, right? Or diameter divided by 2. So when I ask you to calculate the volume, we can substitute this radius in for the formula for R here in the formula, and we can rewrite this in terms of the diameter. So if I substitute that in, I'm going to have pi. This is going to be d over 2, right, squared times h. And then if I expand it out, this will be pi d squared h over 4. So the first thing again that you have to do is compute the volume of the cylinder. So you're simply going to plug in your average diameter here and your average height, right, that you got from your table, and then calculate the volume. Okay, what about the second part of that question, of question 6? Now we want you to calculate prad for volume. We know the prad for diameter because you calculated it in the table. We know the prad for height, right? So the question is, how do we calculate the prad for volume? So if you remember, right, from the video where we talk about calculating prad when you have a formula that involves multiplying or dividing variables, then if I want to calculate the prad for this dependent variable here, the volume, and in this case, it involves multiplying diameter times height. Since it's diameter squared, you can think of this as diameter times height. And the other thing is, the pi and 4 are exact numbers. They don't have any error. It's just the variables that potentially have error, the diameter and the height. So you can ignore the exact numbers, the pi and the 4. And remember the rule now, if I want prad for the dependent variable volume, well, if I have a bunch of variables multiplied together, I have to add their respective prads. And since it's diameter times diameter, or diameter squared, I have to add the prad for diameter twice. So basically, the prad for volume is going to be the prad for diameter plus the prad for diameter plus the prad for height. Let me move this up a little bit. Plus the prad for height. And that will give you the prad for volume. Okay. So again, to calculate the prad for volume here, it's going to be the prad for diameter. So you're going to take this value, add another one, because you have to add it twice, plus the prad for height, right? So this plus another one plus the prad for height, that would be the prad for volume. Okay, the other thing that we need to measure to calculate density is the mass, right? So we have the volume now in centimeters cubed. Now we need to calculate or figure out, find the mass of the aluminum cylinder. So to do that, we're simply going to weigh it or mass it on a scale, right? So there's an electronic scale, electronic balance in the lab. It has a resolution. You got to be careful here. It's only one decimal place. It's zero point 0.1 grams. So you're going to mass the aluminum cylinder 5 times. Now, probably since the scale is really accurate, you're probably going to get the same 5 values, right? All these will be to one decimal place. So obviously that'll be your average. If that's the case, if these were all exactly the same, that means all your absolute deviations will be zero point 0, right? Or 0 0.0, 0 0.0, 0 0.0, 0 0.0. But then when you average these, remember you can't just use zero point 0 here. You have to use at least the resolution of the instrument for your average absolute deviation, right? If you don't remember that, refer back to the video on Prad. So remember, Prad can never be 0%. So you have to use at least the resolution of the instrument here for the average absolute deviation, which in this case is 0.1. So now to calculate Prad for mass, it's going to be 0.1 divided by your average mass times 100, right? And then that'll be your Prad for mass. Okay. But by the way, so make sure you include the table with all your data here for the mass. This is part of question 11 from the lab manual. And then the second part of question 11 is what we're really here to compute is the density. So here's the last table here. So you're going to compute the density of the cylinder. That's simply going to be the mass divided by the volume. The prad for density, right? And since it's mass divided by volume, you have to add the respective prads, and then the percent experimental error. To review this quickly, let me jump over to the tablet again. Okay, so again, remember density, and usually we represent density by this Greek letter rho here. So that stands for density, is equal to the mass divided by the volume of that aluminum cylinder. So you're simply going to take your average mass divided by the volume that you computed, and that will be your density. Okay, for the second part of that table, you want to find the prad for density. So prad for rho, right, for density. Well, remember, it's the same rule as previously. If I want to find the prad for this dependent variable here, in this case density, if the formula involves either multiplying or dividing, this is true for either multiplying variables together or dividing variables, then the rule is you always just add the respective prads. So in this case, to find the prad for density, you're simply going to take your prad for mass, which you calculated earlier in the previous table, plus your prad for volume, which you calculated earlier. And that will be the prad for density. And then finally, the last thing you have to compute is the percent experimental error. So percent experimental error for density. And that's when you want to compare your experimental value. I'll call this like EXP for experimental value. So that's your row experimental to the accepted gold standard predicted value, which in today's lab, we're going to assume is 2.70. So the if you look this up on Google or something, the accepted value for the density of aluminum is 2.70 grams per centimeters cubed. Okay. Yeah, by the way, I should mention the units here, right? Since density is mass divided by volume, remember our mass we measured in grams in this lab, and the volume was centimeters cubed. So it's grams per centimeters cubed. So to compute the error, you're going to take your experimental value for your density minus the accepted value, which I'll just write as 2.70. But remember, we don't really care how we subtract that because we're making it positive. So it really doesn't matter what order you subtract in. You're going to take the absolute value. But the key thing is, what do I divide by? What's in the denominator here? It's always going to be the accepted value, right? The accepted theoretical predicted value, which in this case is 2.70. And then to make that ratio a percent, I just multiply by 100, right? So this will end up being a percent. So that'll be your percent experimental error for the density. And that could be zero, right? If you calculate your density and you got exactly 2.70, then this could be 0%. And that's great. That's fine. For error, it's okay to have 0%. It's only PRAD that we can never get 0%. Okay, and then once you have that, then the first part of the lab is done, right? The density of aluminum cylinder, that part of the